Hi, and welcome to Chapter 4.3, Cautions about Correlation and Regression. Today we're going to talk about the question of causation. Now, association and causation, I'm sure you've heard this many times, there's a big difference between association and causation. There's an association between shoe size and reading index, as people with a higher shoe size tend to read better than people with a lower shoe size. And that doesn't mean someone with a high shoe size is a better reader. What the lurking variable here is age. As people get older, their shoe size gets larger, and they get better and better at reading. Also, mortalities per 1,000 live births. Over time, that number's been dropping, but it's not time that makes that a better, makes mortalities decrease. It's probably increased technology and awareness um, in the medical community. So since there's an association in both of these, but that doesn't mean one causes the other. However, some studies we want to find the existence of causation. We want to find out if drinking alcohol causes a decrease in coordination. We want to know if smoking causes lung cancer or tanning causes lung cancer. This could have a huge impact on people's lives as to what they choose to do. Now, here an example of association is high freshman GPA is associated with high SAT scores, or lung cancer and smoking. We know that there's an association, but it's hard to tell if one causes the other. Now, there's three types of associations that we're going to look at. One is causation, where one thing causes another thing to change. Uh, in common response, there's some lurking variable. The common thing is ice cream sales and murder. So as ice cream sales increase, murder also increases. Now, there's something that affects both of these, and that is the heat. As it gets warmer, there's a higher ice cream sales and there's a higher murder rate. Now, confounding variables means that y is being affected, and it might come from x, and it might come from z, or it might come from 100 different other variables. An example of something that would be confounding would be test scores. So if we have test scores that are increasing, we don't know if that's coming from, say, parents' background, so maybe parents' previous um, uh, maybe parents' level of education, so parents' education level, or it might come from maybe new teaching techniques or interventions, say teaching interventions. There's many things that increase test scores, and just because one year the test scores come up, it doesn't mean that it's the teaching. It might be actually the kids have parents that have gone further in school, or there might be other variables in there that are that are confounding. We don't know what exactly causes the higher test scores. All right, so this goes into a little bit more detail. A causation relationship exists when the change in the explanatory variable affects the change in the response variable. Remember, explanatory is x, response is the y. Even when a direct causation is present, it is rarely a complete explanation of the association between the two variables. The best evidence of causation, well, we need to do an experiment to control all of the different variables. And so I'll read this. If an experiment can change the explanatory variable and eliminate all other factors on the response variable, we can see the direct effect of x on y. But it's very hard to eliminate all of those other variables. A very good experiment can do that, though. Now, this is the common response. We have to beware of these lurking variables that both affect the x and the y. Uh, we need to, before we say one thing causes another, we have to think about all the other things that could be lurking out there. For instance, TV and life expectancy. For the world's nations, let X be the number of TVs per person and Y be the average life expectancy. There's a strong positive correlation between two variables. Nations with more TV sets have a higher life expectancies. Could we expect to lengthen the life of the people of Rwanda by shipping them more TVs? Now that seems ridiculous. Uh, it's the wealth of the nation. If the nation is wealthy, they have better medical practices and more TVs. So there's where a lurking variable could be. A confounding relationship occurs when two variables elicit the same effect on the response variable. Either the variable could be an explanatory or a lurking variable. It's said that education level and life expectancy are strongly positively correlated. Yearly salary also has almost the same effect on life expectancy. So we don't know which variable causes it. It could be neither, but we can't say that it's one or the other. An association between the predictor X and the response Y, even if it's very strong, is not good by itself. It's not good evidence that changes in X actually cause changes in Y. So we always have to look really carefully when we use the word cause. So establishing causation, because sometimes we want to say one thing causes another. It appears that lung cancer is associated with smoking. So how do we know that both of these variables are not being affected by some observed third lurking variable? For instance, what if there is a genetic predisposition that causes people to get both lung cancer and become addicted to smoking, but smoking itself didn't cause that lung cancer? Uh, we can evaluate this association using 5 criteria. So this is the 5 criteria for trying to say one thing causes another. The association must be strong, consistent, and higher doses are associated with stronger responses. So if someone smokes 1 cigarette a day versus 2 packs a day, we would want that person with 2 packs a day to get lung cancer more. The alleged cause precedes the effect. If they have lung cancer before they start smoking, then that doesn't help us out. And the alleged cause has to be plausible. Now, the only compelling method is a designed experiment, and we'll learn a lot about that in Chapter 5. And there's some tough issues that can't uh, we can't do an experiment on, like does gun control reduce violent crime, or does living near power lines cause cancer? Does smoking cause lung cancer? It's hard to take 100 random individuals, tell 50 of them to smoke and 50 of them to not smoke, and wait 80 years to see which ones die of cancer and which ones to not die of cancer. Or have people live near power lines and randomly choose them. People want to live where they want to live. So it's hard to develop some experiments. All right. Now, here are some cautions before rushing into correlation and regression analysis. Do not use regression on inappropriate data, so make sure your data is making sense. Look for the pattern in the residuals. Look for the presence of large outliers and use your residual plots to help that out. Beware of your lurking variables. Avoid extrapolation. So if my data set goes from 40 to 60, we can interpolate, that's this word here, what happens at 55. However, it's not a good idea to guess what's happening out at 80, because maybe your data is really good here, but over here it might level off. So extrapolating is not a good idea. Recognize when correlation regression is performed on averages, and then a relationship, however strong, does not imply causation. All right, here's your homework for tonight. Good luck.